Hello, my name is Steven Varumas. I'm a research associate at the University of Kent in England. And in this talk, me and my colleague Joe Harrison will be presenting the work that we have been doing with Ruben Rowe and Simon Thompson about an automated approach for applying API migration refactorings across an entire OCaml codebase. So here is the outline of this presentation. We will first quickly introduce Rotor, the refactoring tool to which our work is applied. Then we will describe our generic approach for implementing value-based refactorings across OCaml codebases. Then we will look at a case study where our goal is to transform the return type of a comparison function coming from Jane Street libraries. We will then address the issue of applying automated refactoring in the presence of PPX preprocessors, and finally we will talk about some interesting ongoing and future work. So our work is built on top of Rotor, which is an automated refactoring tool for OCaml. Some of you might already be familiar with this tool as it has been previously presented in the 2017 OCaml Workshop. It is a command line tool which is able to automatically rename OCaml identifiers such as function names or module names across entire OCaml codebases. For example, using the rotor rename command followed by the path of the identifier to rename and its new name, the code showed on the left is transformed so that the f function in module A is renamed to g, as it can be seen on the right. Note that Rotor does not simply apply a search and replace algorithm to the source file, but is instead aware of semantical aspects of the program and keeps track of the dependencies between values in an OCaml code. Moreover, Rotor provides a trustworthy approach to renaming, as its correctness has been guaranteed by a code formalization and proof explained in the PLDI paper in 2019. So to use Rotor, the OCaml files of a codebase need to be compiled with the bin_anot flag in order to produce CMT files that contain a binary representation of each file type tree. Then, when Rotor rename is run, these CMT files are first parsed by the tool, and their corresponding typed ASTs are visited in order to calculate a set of file dependencies that will need to be visited too. For each of these files, a replacement set is then generated, and once done, Rotor outputs a patch file representing the changes that need to be applied to the codebase, and eventually this patch file can be applied to the source files, and the refactoring is done. So the currently available version of Rotor is only able to rename values. Thus, our main goal for our work is to extend Rotor to other refactorings, especially to other interface level refactorings. These refactorings can be seen as changes to an API where the signature of a function is modified, and as a consequence, an entire codebase must be updated to take this change into account. As a matter of fact, these kind of refactorings can be achieved by using an approach that consists in a shallow redefinition of the function, meaning a redefinition of the function that only changes its interface but not its body, and a combination of two sub-refactorings. The first sub-refactoring is the injection of a specific lambda expression at the call sites of the function to refactor. This lambda expression, that we also call an adapter, implements the semantics of the refactoring. The second refactoring is the beta reduction of the newly added lambda expression in order to clean up the resulting code. Note that this sub-refactoring is not necessary for the entire refactoring to be correct. One could only apply the lambda expression injection step, and the entire codebase would already have its wanted semantics. However, the process of beta reduction can greatly improve readability of the code, is more acceptable to the user, and can even improve code performances by removing some unwanted closures. The example shown on this slide represents a use of our approach to apply a refactoring that swaps the arguments x and y of a function f. And here, the old application f12 is eventually replaced by f21 as wanted. And I will now let Joe present you a more detailed example of applications of our approach in the following demo.
I'm going to show you two of the value-based refactorings that we've implemented in Rotor, and I'm going to do it on this small code base. We have a mymath module, which defines three functions, a corresponding interface file, and we have another module which opens the mymath module and makes use of the sub, abs, and add functions. Note that on line 9, the name sub refers to the let binding on line 7 and not to the sub function defined in the mymath module. The first refactoring I'm going to apply is I'm going to swap the arguments x and y of the sub function. To do this, I'm first going to compile the codebase because Rotor requires access to the compiled artifacts. Now I'm going to invoke Rotor with the swap_arg command. I'm going to give it the name of the module, which is mymath, the name of the function, which is sub, and then the index of the two arguments that we're swapping, in this case 1 for x and 2 for y. Rotor produces a patch file. This is similar to what you might get in a git commit. What I'm going to do is I'm going to run the same command again, but pipe the output of Rotor straight into the patch command, which is going to change the files on disk. The result of the refactoring is that the arguments x and y have been swapped in the definition of sub, and that each call site has now been replaced with an anonymous function which is responsible for swapping arguments before calling sub. This has also been done in the other file which imports and uses the sub function from mymath. As you can imagine, if you applied lots of refactorings like this, your codebase would become quite unreadable because of the large amount of anonymous functions that get introduced. To deal with this, we've annotated these anonymous functions with the Rotor reduce attribute. And if we invoke Rotor again with the reduce function, it's going to try and eliminate these anonymous functions by performing beta reduction. So let's do that now. First, I'm going to compile the code again. Now I'm going to invoke Rotor with the reduce command, and I'm just going to pipe it straight into patch again. The result is that the arguments 0 and x to this call to sub have been transposed, and in this partial application on line 7 we still have an anonymous function that's responsible for swapping the arguments. The final refactoring I'm going to show you is function inlining across files. In this case, I'm going to inline the abs function, which contains a call to the sub function from the same module. So the first thing to do is rebuild our code, then invoke Rotor with the inline command, give it the name of the module, which is mymath, give it the name of the function, which is abs, and again piping straight into patch. You'll see that now we have an anonymous function at the call site to abs, and that the call to sub is now fully qualified, because otherwise sub would refer to the let binding on line 7 and not to the function defined in mymath. These are just some of the value-based refactorings that we've implemented, but they all follow the same general approach of first applying a refactoring which introduces anonymous functions and then beta reducing wherever possible.
We will now look at a case study where we apply our approach, the Jane Street compare functions. So as in OCaml standard library, the compare functions in Jane Street libraries have a somewhat problematic return type. For each two arguments of type t, they return an integer -1, 0, or 1. This can lead to code that, while being well typed, is semantically wrong. For example, where the result of compare is tested to be equal to 42, which can never happen. So, in our opinion, a cleaner implementation of the compare function should return a data type which only has 3 constructors, less, equal, and greater. And we will use our previously presented approach in order to change this return type of this compare function to odd.t. So here is the procedure for doing this refactoring. It follows 5 consecutive steps. The first 2 steps are not automated at the moment and need to be done by the programmer. Firstly, the programmer must provide a new compare new function of the new type, but they need to leave the old compare function unchanged. Secondly, the programmer must then modify this old compare function so that it is not defined in terms of the new compare function. Thirdly, Rotor is run, and it inlines calls to compare, which introduces calls to compare new across the entire code base. Rotor can then perform beta reduction in order to clean up the code base. And finally, as an optional step, Rotor can be asked to remove the old compare function, which is now unused in the code base, and replace it by the new one. In our case, most of the Jane Street compare functions are in fact automatically generated by the ppxcompare preprocessor, where an annotation to a type declaration leads to the generation of a compare function for this type at compile time. And an issue we found with this is that Rotor is not aware of metaprograms. So the macros of the PPX preprocessors have already been expanded in the CMT files that Rotor uses. So applying Rotor on a code base with PPX macros can lead to the generation of a wrong patch file which references the inline code of the macros, which is not present in the source file. We thus propose two possible approaches to fix this issue. The first one is to expand the PPX macros ahead of time and then refactor the code. However, this solution makes the code base out of sync with the PPX and forces the user to manually update the expanded macros. The second one consists in changing the PPX preprocessor so that it does the first two steps of our procedure automatically, and to mark in the AST with an annotation, for example, what has been automatically generated, so that Rotor can ignore it. And I will now let Joe present you an example of his compare transformation procedure in the following demo.
Let's look at how Rotor interacts with preprocessors. To do this, we'll make use of the ppx compare library, which generates comparison functions for user-defined types. Here, we have a type T, which is either A or B or C, and makes use of the deriving compare attribute to instruct ppx compare to generate a comparison function at compile time. We have an identical interface file, and we also have a usage of the compare function in another module. As an ancillary file, we also have an OR type, which is less, equal, or greater, a toInt function, and a fromInt function. Let's start by building our project. If we try to use Rotor on this codebase, we'll see that things go wrong quickly. So here I'm attempting to rename compare to compare foo. This is the function that is generated by the macro. We see that the call site to mylib.compare is updated correctly, but everything else is wrong. In the ML file for type T, it's been completely replaced by compare foo, and in the interface file, the name T has been replaced by compare foo. Obviously, this won't compile. We can see what's going wrong if we look at the AST produced by the compiler after macro expansion. Here we see the beginning of the definition from the compare function as generated by ppxcompare. We can see that the location information states that this is on line 2, column 0, to line 2, column 16. However, if we look at mylib.ml, we see that that location is actually where the type T is defined. Therefore, when Rotor goes to generate a text replacement, it uses this incorrect location information. We would expect to see this AST node marked as a ghost, which would tell us that this is not present in the source file, and we could choose to either ignore it or generate an error. Let's make a small change to our source code by inlining the output of the PPX preprocessor. I've made a small change to the source files. We now have deriving inline instead of deriving, and we have this end attribute. What's going to happen is June is going to inline the output of ppxcompare for us. Now the compare function has materialized in our source files. If we were to build this and pass the output to Rotor, it would have real location information because the code really exists in the source files. Now let's imagine something different. Let's imagine that we had made a refactoring to the ppxcompare definition itself. Assume now that the ppxcompare library generates two functions, a compare new, which uses the ORD type, and returns or.t instead of an int, and the existing compare function, which is instead a wrapper for this compare new function and still returns type int. This means that no changes need to be made to all the call sites. However, we can eliminate the compare function entirely from our codebase by inlining it. Let's do this. Now, we see that each call to compare has been replaced by an anonymous function which contains the body of compare itself. This means that we can actually now remove compare from our codebase completely. Instead of doing this manually, you can imagine that you updated the definition of ppx compare to achieve this. Our code still builds, and we've now completely eliminated all references to the old compare function with the old type. As a further step, we could even perhaps rename the compare new function back to compare.
So here are some results about us applying the compare refactoring to the Jane Street base library. It takes a few seconds to run any Rotor refactoring over this library. This time is mostly taken by calculating dependencies, and it also includes visiting the AST and generating the correct replacement. Since they are all dependent on each other, a single refactoring that renames a compare function in base leads to 83 changes over 26 different files. As we said earlier, if the ppx compare microcode is inlined, these macros are handled with no issue. However, base still does not compile afterwards because it makes use of some features of the language that are not yet well handled by Rotor, such as some module inclusions and functor applications. This leads to bugs in the dependency resolution, where some compare functions are not replaced as they should be. And we were able to fix some of these bugs, but others are still ongoing. At this moment, compiling the base library still requires some manual fix-up. And in addition to fixing these bugs, we are working on interesting ongoing features. The first one consists in preservation of the code layout after refactoring. The aim is to keep the code of arguments as untouched as possible when we are beta reducing a lambda expression. And this can be tricky in the presence of overlapping text replacement. Another interesting feature is the automated generation of the code for the adapter function. While the implementation of the new function is specific to each use case, the definition of the old function in terms of the new one is rather trivial, since it is only a thin wrapper that does type conversion. It might thus be automatically generated by Rotor. After inlining and reduction, the code is still left with type conversions. For example, the function that changes or.t to integers for compare, which might often be unneeded in the end. A data flow analysis or application of substitution patterns could help us remove most of them. And lastly, we would like for any change in an API to lead to the generation of migration files that would be handled by Rotor, which would automatically update all of the calls to this API accordingly. So, in conclusion, our work provides a powerful automated tool that is able to refactor code across large OCaml code bases while being aware of the structure of the code, a generalized approach for API migration by using injection of lambda expressions and beta reduction. And at the moment there are still some limitations, as Rotor is not yet able to handle all the advanced features of the OCaml language, and refactorings in the presence of metaprograms can lead to inconsistencies mostly if the PPX extensions don't properly mark the code that has been automatically generated. And finally, we are working on promising work which would provide layered preserving refactorings that would seem to have been manually achieved while having been, in fact, automatically generated by Rotor. So we are excited to hear your feedback on this work, and I thank you for your attention.